Let's take all of these gas law problems and develop the critical skills necessary to solve them. So this is 33. A particular balloon is designed by its manufacturer to be inflated to a volume of no more than 2.5 liters. If the balloon is filled with 2 liters, that is our V1, our first volume. V1, 2.0 liters of helium at sea level. And at sea level, the atmospheric pressure, the external pressure, will be 1 atm. If it's released and rises to an altitude at which the atmospheric pressure is only 500 millimeters mercury. So that's going to be our second external pressure, 500 millimeters mercury. We could use 760 millimeters of mercury here. That would have made things simple, but here we can also convert to ATM. And notice if it rises to that atmospheric pressure, will the balloon burst? Assume that temperature is constant. So temperature is constant and the balloon is sealed, so moles are constant. We will use our change in gas equation. So P1V1 over N1T1 is equal to P2V2 over N2T2. And since moles are constant and temperature is constant, right, we just have this equation right here. And solving for the variable that we require, V2, right, we can set this up and substitute in our values. And if V2 is more than 2.5 liters, that designation by the manufacturer, then our balloon will burst. Next problem. 34. A balloon is filled to a volume of 7 times 10 to the second milliliters at a temperature of 20 degrees Celsius. The balloon is then cooled at constant pressure to a temperature of 1 times 10 to the second Kelvin. What is the final volume of the balloon? Again, identify all of your variables. So initial volume, V1, is that given milliliters? Of course, I can convert that to liters as shown. And a temperature, T1, is given, and I'm converting that directly to Kelvin. And then notice that the final temperature is also given in Kelvin, 100 Kelvin, T2. What is the final volume of the balloon? So we are solving for V2, and we should note that the balloon is sealed, so moles are constant, and it was cooled at constant pressure, so pressure is constant. So using our change in gas equation, P1V1 over N1T1 is equal to P2V2 over N2T2, we can eliminate the constant variables, and we get V1 over T1 is equal to V2 over T2. And solving for V2, the final volume, we get this equation, and we can substitute to solve for the missing variables. It is important to note that when you're working with these units, you must always convert temperature to Kelvin. And that's because that's the only one that Celsius and Fahrenheit are in a relative scale. You need to convert that to the absolute scale. You could, however, have kept liters in milliliters, and that would have given us V2 in milliliters. Next problem. 36. Consider the following chemical equation where 2 NO2 gas yields 1 N2O4 gas. If 25 milliliters of NO2 gas is completely converted to N2O4 gas under the same conditions, what volume will the N2O4 occupy? So again, this volume is our V1, and we are solving for V2. And it appears as if there's no other piece of information, but it is completely converted. So in this equation, we have 2 moles of NO2 gas, and we are completely converting that to 1 mole of N2O4 gas. And it's important to note that when we're talking about ideal gases, the whole point of talking about ideal gases is that gases behave in this ideal sense as if they're all exactly the same, that they have no unique chemical properties. Of course, this is not how real gases behave, but we'll discuss that in following unit. But that's really only under extreme conditions. Under really normal, quote-unquote, conditions, most gases will behave very, very similar to each other. So going from 2 moles to 1 mole, that's our N1 and N2. And then it says under the same conditions, so then we have temperature and pressure constant. Of course, we can bring our change in gas equation and solve for the missing variable. 40. A flask that can withstand an internal pressure of 2500 torr, but no more, is filled with a gas at 21 degrees Celsius and 758 torr and heated. So the flask will not change its volume. So volume is constant, and it's filled with a gas. Of course, we're assuming that that is then closed because it is heated, and we're looking for what temperature will it burst, right, under that pressure. So then moles are constant. So that's a sealed flask. Moles are constant. V is constant. So we're given T1, the initial temperature, and we're given T. We're solving for T2, so that's a typo there. So we're given T1 and P1, first pressure, and we're given P2, the second pressure. We're solving for what temperature will that pressure of the gas meet this and therefore burst the flask from the inside out. 41. If a 2.5 liter container is filled with 175 grams of argon, and now we have two conditions. So notice the volume is given, the volume is given, and then the grams of argon. And you should immediately note that we can convert the grams of argon using the molar mass of argon to moles of argon. If we have volume of argon, we have the moles, and we have the pressure, we can easily solve for the temperature using our ideal gas law equation. Since there is no change in the gas, we're just describing the properties of the gas, we're going to use PV equals nRT. And so T would be equal to PV divided by nR. And we would just substitute and solve for temperature. Of course, that temperature will be in Kelvin. And make sure you have the right R value, which is 0.08206 liters atmosphere per Kelvin mole. 42. A person accidentally swallows a drop of liquid oxygen, O2, in the liquid state, which has a density of 1.149 grams per mil. Assuming the drop has a volume of 0.050 mils, what volume of gas will be produced in the person's stomach at body temperature, 37 degrees Celsius, and a pressure of 1 atm? Do not confuse this volume right here with the volume of our gas. That is not the same. That is the volume of the liquid, and the liquid has a density of this. So we're going to use the volume and the given density to find the grams, and then use the molar mass of O2, not O, but of O2, to find the moles of O2 in that drop of liquid oxygen. If we have that moles of O2, that will be all the moles of O2 that will turn into the gaseous state inside the person's stomach. And so if we have moles of O2 and we have the temperature converted to Kelvin and the pressure, we can solve for the volume using our ideal gas law equation. 43. A gas sample containing 1.5 moles at 25 degrees Celsius exerts a pressure of 400 torr. The missing variable here is, of course, volume. And so we can again use our ideal gas law equation to solve for that volume. So notice moles, temperature needs to be converted to Kelvin, and here's that torr, that pressure needs to be converted to atm because PV equals nRT uses the R value, and the R value is 0.08206 liters atmosphere per Kelvin mole. So you must convert temperature, always of course to Kelvin, but pressure as well needs to be converted to atm because our R value has that unit in it. So some gas is then added to the same container, and you have the volume of that container now if you use this equation, and the temperature is increased to 50 degrees Celsius. So we have the new temperature. So we have the volume and the new temperature and the new pressure, P. And we're asked how many moles of gas were added to the container. Well, again, we could do a separate calculation for moles because now we have the volume from the previous calculation. We have a new temperature and a new pressure, and we can solve for the moles. So, of course, you need to convert that to Kelvin and this to atm as well. If we solve for the new moles, we can subtract the difference, right? We can find the difference between this moles of gas and the previous moles of gas right here, and that would tell us how many moles were added to the container. 44. A bicycle tire is filled with air to a pressure of 100 psi at a temperature of 19 degrees Celsius. Riding the bike on asphalt on a hot day increases the temperature of the tire to 58 degrees Celsius. So we have this pressure. This is initial pressure P1, and we have the initial temperature T1. And riding the bike on asphalt on a hot day increases the temperature. So this is our new temperature T2, and the volume increases by 4%. So that means that we actually have both V1 and V2, given that V2 is equal to 1.04 times V1 because it increases by 4%. So the V2 is equal to 1.04 times V1. So what is the new pressure? We're finding P2. Of course, we're going to use our change in gas equation because we have all of these variables, and we can substitute, of course, the moles. Since it's a sealed bicycle tire, moles are constant. Consider two separate gas containers in the following conditions, right? It's container 1 and container 2. And notice in container 1 we have moles, volume, temperature. We don't have pressure. So of course we can solve using the ideal gas law equation. Again, this is one gas and this is another gas. So we should use the ideal gas law equation. So P is equal to nRT divided by V. Of course, we should convert temperature to Kelvin, but we've got volume in liters and moles already given, so we can solve for the pressure there. And then we would have to do a separate calculation for container B, using, again, the ideal gas law equation. And so solving for that pressure, right, then we can relate the pressures to each other in a ratio. Finally, 46. A container is filled with an ideal gas to a pressure of 40 atm, so that's our pressure, and at 0 degrees Celsius, that's our temperature. What will the pressure of the container if it is heated to 45 degrees Celsius? So what's constant here? Again, a container is filled, and so we're assuming that moles are constant because that's sealed, a sealed container, and that container is fixed, right? So that's volume constant. So the only things that are changing here is here's our pressure P1, and we're looking for P2. We have T1 and we have T2. So notice again how this differs from using this equation, because this is one gas that is undergoing a change. So we've got, again, P1, we're solving for P2, we have T1, and we have T2. B is a separate calculation. Again, we have P1 and T1, and we're looking for T2 if P2 is this. And C is similar there. Till next time.